Reality is merely an illusion, albeit a very persistent one. Albert Einstein. Imagine that our existence is not what it seems, that what we perceive as reality is, in fact, an exquisitely crafted video game. Welcome to the mind-bending realm of the simulation hypothesis, where the line between reality and virtuality fades into a cryptic web. As we venture into this intricate web of possibilities, we ponder the fundamental question: are we merely characters in a grand, multiplayer online video game? Brace yourself for a journey that will push the boundaries of your imagination. Even though the term simulation argument was coined by Oxford philosopher Nick Bostrom in Landmark paper in 2003, the idea of living in a simulated reality has been present in science, religion, and fiction for a very long time. One of the earliest examples of this concept can be found in Plato's book, The Republic, where he talks about a cave and its inhabitants. In this cave, people are chained to a wall and can only see shadows of objects cast by the light outside. They create their own understanding of reality based on these shadows, and Plato surmised that we are like the residents of this cave, seeing only shadows of the real world. Similarly, many religious beliefs suggest that the world we see around us is not entirely real. According to Gautama Buddha, who founded Buddhism, our existence in this world is like an illusion caused by ignorance. To explain this, he uses the analogy of a small puppy tied to a strong pillar with a steel chain. The puppy can only move within the length of the chain, just as beings are confined by 5 aggregates: form, sensation, perception, volition, and consciousness. The chain that keeps them restricted is their craving for these aggregates. However, by eliminating ignorance and desires, beings can free themselves from this illusory existence and reach the place beyond called nirvana. This thought-provoking insight suggests that the world we perceive may not be as real as it seems, and there could be an entirely different existence beyond this illusion. Psychiatrists like Carl Jung have probed the question of mental projection, where each person interprets the world slightly differently based on their inner thoughts. In this perspective, a significant part of what we consider the external physical world is, surprisingly, a product of our own minds, resembling a vivid dream, without any concrete objective physical reality. More recently, Elon Musk has popularized the simulation hypothesis, suggesting a 1,000,000,000 to 1 chance that we live in a sophisticated simulation rather than true physical reality. In the realm of science fiction, no other movie was more influential in popularizing the simulation hypothesis than The Matrix, released in 1999. The film portrays Keanu Reeves as Mr. Anderson, inhabiting a world similar to ours. However, during the night, he transforms into the skilled hacker, Neo, who explore various virtual realms on the internet, only to uncover enigmatic references to something known as the Matrix. This revelation leads him to encounter a group of hackers who challenge his entire perspective. In a now iconic scene, Neo is given a choice of taking the red pill or the blue pill by a character called Morpheus. The red pill will wake Neo up, while the blue pill will allow him to continue living his existence in the dream world. That is the Matrix. Opting for the red pill, Neo wakes up to the realization that his perceived reality was a computer simulation. He discovers that in the real world, humans are living in pods connected to the Matrix in a highly realistic video game-like simulation. The sequels to The Matrix reveal that this simulated reality was designed by super-intelligent machines to keep human minds occupied, which were using the small amount of electricity generated by each human's brain for their own nefarious purposes. Quantum physics offers compelling evidence, hinting at the possibility of a simulated reality. The core of quantum physics lies in the idea that the universe isn't continuous, but rather composed of discrete units known as quanta. This holds true even for subatomic particles like electrons, which appear to instantaneously jump between states without going through the values in between an occurrence known as a quantum leap. Interestingly, this behavior also mirrors computer simulations, which rely on discrete units called pixels. Among the fascinating and perplexing aspects of quantum physics is the notion that our existence may not be rooted in a physical universe as conventionally understood, but rather in a realm of probabilities. According to this idea, subatomic particle exists as a wave of probabilities, which is called the quantum probability wave, until wave collapse into a singular reality. A helpful analogy compares it to being in a theater with multiple seats, where the wave represents the probability of occupying any particular seat. Quantum physicists propose that consciousness plays a pivotal role in the collapse of the probability wave, acting as a cosmic usher, guiding particles to specific seats in the theater of reality. This concept challenges the notion of a separate observer and observed universe, disrupting the traditional idea of subject-object separation. Moreover, it raises the intriguing possibility that we might not be living in an entirely objective reality. Instead, our consciousness is so interconnected with reality that we may be living in a set of interconnected subjective realities. This phenomenon, known as quantum indeterminacy, stands as one of the most profound and captivating mysteries in the realm of physics. In quantum physics, the collapse of a probability wave into a single future seems to be dependent upon conscious observation or measurement. Drawing an analogy to a video game, a player's path is determined by their conscious choices, and how those choices are rendered on their own computer can be thought of as machine of consciousness. Each player's computer renders only the relevant portion of the virtual world, based on their individual choices, suggesting that each of us may experience a slightly different version of reality depending on our observations of the world around us. Einstein's groundbreaking work revealed that the speed of light remained a fundamental constant in our universe. But as objects approached the speed of light, both space and time appeared to adapt, a puzzling phenomenon verified by experiments. Einstein's involvement in the emergence of quantum physics brought about a redefinition of how atoms and subatomic particles behave. The discovery of the Pauli exclusion principle by Wolfgang Pauli revealed that no two electrons in an atom could occupy the same position or quantum state simultaneously. Einstein's investigations into the photoelectric effect led to the understanding that light acted as quanta or particles that jump states when absorbing energy, which is called the quantum leap. These quanta of light, now known as photons. These groundbreaking discoveries led to a reevaluation of the Standard Model for describing subatomic particles' nature and behavior. It became evident that electrons and other subatomic particles were not as orderly as previously believed, dismissing the notion of continuous orbits in the planetary model of the atom. The ideas of pinpointing the exact position of electrons become impossible, leading to the realization that it existed in a cloud of probabilities. The more one tried to pinpoint a particle's location, the less certain its speed became, and vice versa. The crux of the problem lies in the dual nature of certain particles in the quantum world, where a particle can be both a single particle and a wave at the same time. Visualizing this, we can think of a particle as being confined to one specific location, similar to a person who's sitting in one chair in a movie theater. This is what we call the local nature of a particle. On the other hand, a wave can show where a particle might be found based on the probability of each location. To illustrate this, imagine this wave representing the set of probabilities that you will choose any particular chair in the theater to watch the movie. Each point on the wave indicates the likelihood of the particle being present at that point. The famous double-slit experiment was designed to investigate whether particles, for example electrons or photons, behaved as discrete particles or as waves. If they behaved like waves, they would pass through both slits and create an interference pattern on the screen beyond. If they acted as particles, they would go through just one slit at a time and appear at specific positions on the screen. Unexpectedly, the double-slit experiment revealed that basic particles such as photons and electrons demonstrated both wave and discrete particle behavior, and their exact locations could not be determined until we observed it. To further illustrate this, imagine a dark theater with only a single flashlight to illuminate one chair at a time. or all the lights switched on simultaneously. When the flashlight targets a particular chair, the particle appears only in that specific chair. However, when all the lights are on, then we would see the wave or partial presence of the particle appears across all chairs. This showcases the peculiar behavior of quantum particles. Early quantum scientists referred to this wave of possibilities as the quantum probability wave, and they proposed that when a particle is observed, the wave collapses into a single possibility. The cause of this collapse remains a debated topic to this day. Heisenberg asserted that the path of the electron comes into existence only when we observe it, while Amit Goswami, a retired physicist from the University of Oregon, suggested that measurement reduces the electron wave to a particle state. This central dilemma of particle-wave duality raised profound questions not only about the classical model of the atom, but also about our fundamental understanding of scientific observation and the separation between subject and object. Modern science is built on the idea that the observer and what is observed are separate, and that the act of observation doesn't affect the outcome. However, quantum physics challenged this notion, suggesting that observation does play a role in collapsing the probability wave. This means that the observer, who is a conscious entity, is participating in the outcome of the results of physical phenomena, at least at the subatomic level. In 1935, physicist Erwin Schrödinger was attempting to explain the concept of quantum superposition, where a particle can exist in multiple states simultaneously until observed, at which point it assumes one state. To illustrate this idea, Schrödinger used the example of a theoretical cat in a box with a radioactive substance that has a 50% chance of killing the cat. Before opening the box to check, we don't know if the cat is alive or dead. Quantum physics indicates that the cat is in a superposition of both states until observed, and only then the outcome becomes definite. The concept of superposition can be puzzling, as it means an entity can exist in multiple states at once, until observation determines a specific reality. This idea is also observed in the behavior of subatomic particles like electrons, which exist as waves of possibilities until observed, at which point they become localized particles. Taking a step forward, John Wheeler, a renowned theoretical physicist, introduced additional choices after the two slits in the experiment. This move was an attempt to appease certain physicists, who believed that the particle had already assumed either a solid particle or wave state when passing through the slits, and the measurement just told us which one after the fact. This comparison can be likened to Schrödinger's cat, already being either dead or alive. It couldn't be both. Opening the box in the future merely reveals to us the cat's actual state. This Wheeler-proposed experiment, known as the delayed-choice experiment, is a continuation of the original double-slit experiment. In this setup, after the particle passes through one set of double slits, there is a mirror that reflects the individual particles in another configuration. If the particle behaved as a particle when it passed through the slits, its behavior would differ from a wave. Although Wheeler initially posited this theoretically, scientists later found ways to implement it. In one configuration, a lens is placed after the slits, causing the particle's path to diverge upon contact with the lens. This means that if a particle goes through slit 1 or slit 2, it will have a different destination, that is telescope 1 or telescope 2. Strangely, when an interference screen is briefly introduced between the lens and the telescopes, an interference pattern appeared, indicating that the particle behaves like a wave, passing through both slits. However, the particle cannot reach the telescopes unless it acts as a discrete particle, passing through only one slit. This led to two paradoxical results: the presence of an interference pattern and the particles arriving at one telescope or the other. Wheeler concluded that quantum particles are undefined until the moment they are measured. Even if the measurement happens after, the particle needs to make a choice of which slit to go into. This notion challenges our perception of reality, likening it to Schrödinger's cat not being dead or alive until observed. In 2017, Italian scientists conducted a delayed choice experiment over long distances by bouncing lasers off of satellites, yielding consistent results. Surprisingly, the photon exhibited both wave-particle properties until the moment of measurement, which means that something in the future, the observation, was influencing something in the past, a concept termed retro-causality. Some experts who have taken this implication to the macro level believe that the delayed choice experiment implies that we might exist in multiple probabilities at once, both in the present and the future. This suggests that the probability waves in quantum physics not only describe where particles or individuals are now, but also where they might be in the future. If the concept of the future influencing the past sounds like something out of science fiction, then the many worlds interpretation of quantum physics takes it even further and has become the inspiration for numerous science fiction and fantasy stories. Proposed by Hugh Everett, this interpretation suggests that when a quantum choice is made, instead of a probability wave collapsing into a single reality, multiple universes are created, each representing a different outcome. In these parallel universes, all the probabilities are true, leading to a vast multiverse of infinite possibilities. The term many worlds interpretation, MWI, was popularized by theoretical physicist Bryce DeWitt, gained popularity through his articles in the 1960s and 1970s. DeWitt wrote in a famous explanation, "Every quantum transition taking place on every star, in every galaxy, in every remote corner of the universe, is splitting our local world into myriads of copies of itself." The idea is mind-boggling. Every quantum transition, no matter how big or small, results in a branching out of countless universes, each with its own unique set of choices. This means there could be universes where Schrödinger's cat is both alive and dead simultaneously. Now, we simply refer to this idea as the multiverse. While this theory may seem far-fetched, it offers a compelling alternative to the subjective universe implied by quantum physics. If parallel universes are being created each time we make a major decision, or a minor one, in the realm of quantum physics, then there is a directed graph of multiple universes that are branching out. This would imply that each branch gets branched again, and we end up with an ever-increasing number of universes each time a quantum decision is made. However, one theory, explored in one of Stephen Hawking's final papers, suggests that the number of parallel universes may not be endless but restricted to a smaller count. Despite each quantum decision leading to a new universe, some of these universes are quite alike. For instance, if you choose eggs for breakfast today and sausage tomorrow, these two universes may appear similar from your viewpoint, particularly when contrasted with universes where you make more significant life choices, such as killing someone or becoming a monk. In this complex web of branching universes, you could reach similar states of existence through different paths and choices. For example, you could end up at point C by following two different routes and sets of choices, even though they started from the same point, A. Let's revisit the simulation hypothesis. If we are in a simulated reality instead of a physical one, the question of whether probable future selves or parallel worlds are real or simulated becomes more understandable. A computer can simulate a large number of possibilities very quickly. In fact, this is one of the major ideas behind running simulations. Video games, with their AI capabilities, are capable of branching out possibilities and making decisions based on measured information. Debates exist among physicists and philosophers on the nature of the parallel universes proposed in the many-world interpretation. Are these universes real physical worlds, or just probabilities tracked by a computer? For these copies of the universe to be real, it would mean someone or something has to create a copy of the entire universe every time a decision is made. This is quite a complicated and resource-intensive task. Let's compare this to cloning in biology, where we can create copies of cells or organisms. But remember, cloning takes time and effort. It can't happen in a snap. Now imagine trying to clone the entire universe and making sure every single particle is in the exact same place as before. That's an incredibly complex task, way beyond anything we can imagine. In contrast, the concept of optimization in computation offers a more believable approach. In a computational model, information about the universe exists digitally, and particles or pixels are rendered only when necessary, much like in video games or simulations. Stephen Hawking's suggestion that the number of universes may not be infinite, but limited to the number of particles, implies that many of the particles in the copied universes are in similar configurations. This aligns with common optimization techniques used in computers and computer graphics. As we think about a computational structure that could support multiple universes, many of these universes will have particles in the exact same location, leading to significant compression and optimization. Considering a computational framework for reality opens the possibility of a vast computer system that processes information and renders particles only when required, a form of quantum indeterminacy when needed. Therefore, the theory proposing that all reality is in fact an artificial or virtual simulation might be the only practical way to comprehend the many-world interpretation, the delayed choice experiment, and the concept of future probable scenarios.